Hey guys, this is section 9.11 where we talk about how activities are defined with respect to standard states. So the ideal dilute solution model, it doesn't apply to most solutions. Most solutions aren't dilute ideal solutions. Their concentrations are such that Raoult's law is obeyed for the solute but not the solvent, and Henry's law is obeyed for the solvent but not the solute. We defined activity coefficients to take into account deviations from this behavior, from ideal behavior. Now we're going to make sure that the activities behave properly. That is, they give us ideal behavior in the correct limit. So that means we want, for the solvent, the activity to approach the concentration, or mole fraction at this point, as the mole fraction goes to 1. And the solute, we want the activity to go to the mole fraction as the mole fraction goes to 0. And so when in these limits, the activity becomes close to being equal to the concentration, and we can just use the concentration. We're setting the activity coefficient equal to 1 in these limits. And that makes things a lot easier, because it's a lot easier to find the concentration usually than it is to find the activity of a species. We make the concentration unitless by dividing by concentration of 1. So we say that when we do it this way, the activity calculated with this definition, what we saw in the last section right up here, is based on Raoult's law standard. That means the activity goes to 1 as the mole fraction of the solvent goes to 1. The standard state chemical potential, based on this standard, Raoult's law, is the chemical potential of the pure solvent. So mu solvent, asterisk. However, that doesn't work when we're talking about a solute in dilute solutions, because the solute obeys Henry's law, not Raoult's law. It's a different standard. So we need a different, I don't know if better, but different definition of the activity in the standard state. So we're going to start out writing out the chemical potential of the solute in the solution as the chemical potential of the pure solute plus RT ln of, in place of the pressure over the pressure of the pure solute, we're going to use Henry's law. So what this is right here, guys, is we just replaced P, pressure of the solute above the solution, with Henry's law, which says that the pressure above the solution is equal to Henry's law constant times the mole fraction of the solute. But that's equal to, so if we break this up, into this term and then the mole fraction, our ln of AB is equal to ln of A plus ln of B, right? So that means we can write this as the mole fraction of the pure solute plus RT ln of Henry's law constant over the vapor pressure of the pure solute plus RT ln of the mole fraction of the solute. Or we can write that like this. In this equation right here, we've defined the chemical potential of the pure solute with the Henry's law standard as being these terms right here. All this right here, that's U solute Henry's law. And there it is right there. Writing the activity and the activity coefficient based on Henry's law, the activity is the pressure of that component divided by Henry's law constant for that component, and the activity coefficient is just the activity with its new definition over the mole fraction of that substance. By the way, this also applies to non-volatile solutes, glycerin, sucrose, what have you. So the Henry's law standard, it's one where the pure solute would have a vapor pressure equal to its Henry's law constant. This would be equal to this, and that's purely hypothetical. There's no real life analogy to that, or it doesn't happen really. So let's do an example here. We're going to calculate the activity and the activity coefficient for a solution of carbon disulfide and acetone, with the mole fraction of carbon disulfide in the being 0.1991, We're going to do it using a Henry's Law standard and a Raoult's Law standard. We're given this information, which normally we just look up in a table. Vapor pressure of carbon disulfide under these conditions, is this pressure, 271.9 torr, pure carbon disulfide, 512.3 torr, and Henry's Law constant is 1750 torr. So to find Henry's Law standard activity, just use a definition. This should be the pure substance right here. Like that. And plug it in, we get this number, 0.5307, and the activity coefficient is this activity that we just got divided by the mole fraction, which is this right here, gives us 2.6657 or so. Using Henry's Law constant, we can see we get significantly different numbers. The magnitude of these are different. So the activity with Henry's Law standard, it's a pressure divided by Henry's Law constant, which is this. And the mole fraction is that activity divided by the activity coefficient is the activity divided by the mole fraction. So plug this guy in here and get an answer. Again, way different than the activity coefficient using Raoult's Law standard. Now we can also define the activity and the activity coefficients in terms of other concentration units like molality. To do that, we just define the activity of the solute, let's say, in terms of molality, as going, so that it goes to becomes the molality as the molality goes to 0. And so it would just be the vapor pressure of the solute over the Henry's Law constant in terms of molality. And the activity coefficient, likewise, the activity that we defined up here divided by the molality rather than mole fraction of the solute. And so here the activity coefficient goes to 1. We define it that way so that as the molality goes to 0. We can do this with other units of concentration too. The quiggative properties, the freezing point depression, boiling point elevation, and osmotic pressure we talked about, we can now write those in terms of the activities rather than the concentrations. Give us in regions where we're not in a really dilute solution one way or the other, it gives us a better result. Where here the activity coefficient is, it's just the activity, or rather the activity coefficient times the molality is the activity. So we're writing the activity like that. Same thing here. And here we're using the molarity. This big M stands for molarity, and the activity coefficient there for molarity.